Okay, so welcome to this deep dive. Um, you sent over some really interesting stuff. I mean, there's these notes about content redaction and a little something about the Frontier AI podcast, but then there's this like really in-depth transcript about GPT models.
Hmm.
And I think today, our goal is to kind of pick out those like key insights, those gems from the GPT discussion, and really try to understand why it all matters. Why should people care about this?
Yeah, definitely. It's a lot to unpack.
So we're going to like trace the history,
Right.
look at how these models learn, and even like touch on some of their more surprising capabilities, right?
Absolutely.
We want to like give everyone a clear picture without getting too lost in the technical jargon, make it accessible.
Yeah, absolutely.
And before I forget, they specifically asked for a shout out to the Femtor AI podcast.
Oh,
So
nice.
we'll give them a welcome message and also leave them with a question at the end.
Sounds good.
Okay. And just a quick note, for this deep dive, we need to avoid mentioning Visora or anything labeled Lecture 5. But that YouTube thing, we can call it Episode 8.
Gotcha. Okay.
Okay, so with all that in mind, let's dive right in. Like, let's start at the beginning with the evolution of these powerful language tools. It all started around 2017 with a paper called Attention is All You Need.
Right.
It introduced the transformer architecture. What, what struck you as the most significant thing about that foundational work?
Well, I think what's really fascinating here is this paper really kind of like shook up the world of natural language processing.
Hmm.
Before that, RNNs were kind of the go-to
Oh,
method.
NNs, right.
Recurrent neural networks.
Yeah.
They were like the standard for understanding and generating text.
Okay.
But they had this problem. They really struggled with grasping long-range connections in language. So think about it, like you're trying to understand the very end of a long paragraph, and it refers back to something at the beginning.
Yeah.
RNNs, they couldn't really handle that very well.
Right.
The transformer architecture, particularly its self-attention mechanism, gave models a way to look at all the words in a sentence at the same time.
Simultaneously.
Yeah, and figure out which ones were most important in relation to each other. It was a huge leap forward for things like next word prediction, translations, you name it.
Yeah.
And it actually outperformed those older RNN techniques.
Right.
I think it's also important to remember that the original transformer, it had like two main parts, the encoder and the decoder working together.
Right. It had both of those. So how did that initial design, how did it evolve into what we know as GPT?
Okay, so to connect this to the bigger picture, the arrival of GPT, the Generative Pre-trained Transformer in 2018, it was a direct result of that transformer breakthrough we were talking about. The key change in GPT's architecture, basically, they got rid of the encoder, leaving only the decoder. And you might think, oh, they're simplifying things, right? But actually, this opened up a whole new world of learning, which is what we call generative pre-training.
Generative pre-training.
Yeah.
That sounds like a big deal. Can you break down what that actually means?
Sure. So the fundamental idea behind GPT's pre-training is this thing called unsupervised learning. And it's all about learning from text that hasn't been labeled or categorized.
Okay.
So, traditionally, when you teach a language model something, you need all this carefully prepared data. Like if you want it to translate, you need a bunch of sentences that match up in English and French, right?
Yeah, yeah.
But getting that labeled data, it's slow, it's expensive.
Yeah.
And so GPT has this clever workaround. It uses a sentence itself as its own training data. So imagine you give it a sentence like, the dog barked loudly at the...
Okay, yeah.
And its job is to predict the next word. Probably something like mailman or maybe cat.
Right, right. Makes sense.
Yeah. And by doing this, like over and over again with tons and tons of text, it starts to pick up on the patterns, the relationships in language, without anyone having to tell it what those patterns are. It
Yeah.
figures it out on its own.
That's amazing.
And this was a really big departure from those earlier methods that were so reliant on having all that labeled data.
So it's basically just learning by watching language in action, like in its natural habitat, and just predicting what comes next.
Mm.
That's really ingenious. Now, the name GPT is like everywhere these days. Can you give us a quick overview of the different generations? So we had the original GPT, then GPT-2, GPT-3, and what we have today. What were the big leaps, the breakthroughs with each one?
Yeah, it's been an incredible journey to see this progression. So, as we said, the first GPT in 2018 introduced this whole generative pre-training concept using the transformer decoder,
Right.
and it showed, real promise for language understanding, but it was mostly used in research labs.
Right.
Then in 2019, GPT-2 came along. It was basically the same idea, but like supersized, way more data, much bigger models.
Okay.
The biggest one had something like a billion parameters, and here's where things get really interesting. This increase in size, it actually led to a noticeable jump in performance. The text it generated was more coherent, more relevant, and it really started to grab people's attention, even outside the AI world.
Yeah. A billion parameters, that's a big leap.
Yeah,
And then we get to GPT-3.
right. GPT-3 in 2020, that was a game changer. It just dwarfed GPT-2 with a mind-blowing 175 billion parameters. And this massive increase in scale, it didn't just make next word prediction better, it actually unlocked all these new abilities that the model wasn't even directly trained to do.
Like what?
Suddenly, it could translate languages, analyze sentiment in text, even answer questions with surprising accuracy. It was like, whoa, where did that come from? And they actually released different sizes of GPT-3, to fit different needs.
Right.
And then, of course, the evolution continued with GPT 3.5 and the even more advanced models we're seeing now, like GPT-4. The speed of progress has been just remarkable.
It really is.
Yeah.
Now, in the stuff you sent, there was this mention of zero-shot and few-shot learning. This seems really important to understanding how versatile these models are. Can you explain what those terms mean?
Absolutely. So this gets to a crucial aspect of how these models can handle tasks they weren't specifically trained for. Let's start with zero-shot learning.
Okay.
Imagine you ask the model to do something, and it can do it based only on the instructions you give it without ever having seen a specific example of that task before.
Okay.
Like, say you ask it to translate cheese into French.
Yeah.
Just by saying, translate cheese to French, if it gets it right without having ever seen any examples of English to French translations, for cheese or anything similar, that's zero-shot learning in action.
That's pretty impressive. It's like it understands the request and applies its general knowledge of language to get the job done. And what about few-shot learning?
Okay, so few-shot learning is a step further. Here, you give the model a tiny handful of examples, and then it uses those to figure out how to do the task. So, for example, you might show it one example. The sea otter is a playful animal. Translates to some French phrase.
Right.
Then you ask it to translate, cheese is often made from milk.
Okay.
The model uses that one example to understand what translation is and then applies it to the new sentence.
Yeah, yeah.
The original paper about GPT-3 really highlighted how good it was at this few-shot learning. They showed that just a few examples could make it much better at a whole range of tasks.
So GPT-3 was presented as this, like, superstar at learning from just a few examples. What about the newer models like GPT-4? How do they see themselves in terms of zero-shot and few-shot learning?
It's really interesting. When you ask GPT-4, it actually describes itself as primarily a few-shot learner that also has some strong zero-shot capabilities.
Yeah.
It acknowledges that, while it can handle a lot of tasks just based on the instructions you give it, that's zero-shot, giving it a few good examples usually makes its responses more accurate, more nuanced.
Right, right.
So even the most advanced models, they still benefit from having a little bit of guidance, a few examples to learn from.
Yeah, that makes perfect sense. I mean, even the smartest person can benefit from seeing a couple of examples when they're learning something new. Okay, let's talk about what fuels these amazing abilities.
Yeah.
Data. The amount of data GPT-3 was trained on is just mind-boggling. Can you give us an idea of where that data came from and just how much there was?
The scale is it's crazy. GPT-3 was trained on something like 300 billion tokens. Now, for our conversation today, think of a token as being roughly the same as a word.
Okay, so a word.
Yeah. And this huge data set, they gathered it from all sorts of sources across the internet and even beyond. The biggest chunk, something like 60% of the data, so that's about 410 billion tokens, it came from a project called Common Crawl.
Common Crawl, right?
It's basically a massive archive of web pages, text, code, you name it, from all over the internet.
Wow. So they basically just scrape the web.
Yeah.
That gives you an idea of how much information they're dealing with. What other kinds of data did GPT-3 learn from?
Another big chunk, about 22% of the data, or 19 billion tokens, came from something called Web Text 2. This was a beefed up version of an earlier data set called Web Text, and it specifically included loads of text from Reddit, like posts that people upvoted a lot.
Ah, Reddit. Makes sense.
And then the remaining 19% of the data came from a collection of books and the entire English Wikipedia.
So it was trained on like this massive, diverse collection of text. Everything from random web pages to like classic literature and encyclopedias.
Yeah, that
That really gives you a picture of the huge scope of knowledge these models are exposed to. And all that processing, all that data, the cost of training must have been astronomical. You mentioned a figure for GPT-3's pre-training cost. Can you remind us what that was?
Yeah, the estimated cost to pre-train GP3 was somewhere around $4.6 million.
$4.6 million.
Yeah, it's a crazy amount of money. But it shows you just how much computational power goes into training a model like this. It's all about optimizing those 175 billion parameters, making them better at predicting the next word, and you're doing that with billions of sentences.
Right. It's a huge undertaking. Now, you mentioned pre-training, but your notes also talked about fine-tuning. What's the difference between those two stages?
Right. So pre-training, that's that initial learning stage we were talking about. It's all about learning the basics of language in a broad sense, and it's unsupervised. Fine-tuning comes after that.
Okay.
You take a pre-trained model, and then you train it further on a much smaller data set that's specifically labeled for a particular task.
Okay.
So imagine a company wants to use a language model for customer service.
Right.
They might fine-tune a general model on transcripts of their past customer service calls.
Okay.
So it learns the specific language and vocabulary of their customer service interactions.
Yeah, that makes sense.
And the nice thing is, fine-tuning doesn't need as much data or computing power as pre-training.
So pre-training is like giving it a general education, and fine-tuning is like sending it to a specialized school.
Exactly.
Okay, now, in the world of large language models, there are some that are open and some that are closed. Can you explain the difference between open source and closed source models?
Sure. So models like GPT-4, they're considered closed source. This means we don't really know the details of their architecture, the exact values of those parameters, or the specific data they were trained on.
Right.
It's all secret.
Okay.
You can interact with them, but you can't see how they work under the hood.
Yeah.
But then you have open source models. These are models where all the details are out in the open, things like the Llama family of models. This allows researchers to study them, tinker with them, and it makes the technology more accessible to everyone.
So it's like the difference between having a recipe and just having the finished dish.
Yeah, exactly. And what's really exciting is that the best open source models are catching up to the closed source ones in terms of performance.
That's really encouraging. Now let's go back to the architecture for a moment. We briefly touched on GPT being a decoder-only transformer. Can you unpack that a bit more? How does that differ from the original transformer design?
Okay, so remember how we said the original transformer had both an encoder and a decoder?
Yes.
Well, GPT just focuses on the decoder part.
Okay.
GPT-3, for instance, has 96 of these decoder layers, all working together to make up its 175 billion parameters. The reason for this decoder-only approach is that decoders are really good at generating sequences of data step by step, which is perfect for tasks like language generation.
Right, predicting one word after another.
Exactly.
Okay, 96 layers just for decoding. That's a lot of processing power dedicated to generation. Now, another term that came up a lot was autoregressive. What does it mean for GPT models to be autoregressive?
This is how they actually generate text. Autoregressive basically means it predicts the next word based on all the words that came before it. And then once it predicts that next word, it adds it to the sequence and uses that new, longer sequence to predict the next word and so on.
Okay, so it's constantly building on its own output.
Exactly. It's a chain reaction of word prediction. And during training, it's basically trying to predict the next word in a text. And the actual next word is like the right answer that it learns from.
Right, so even though it's not using explicit labels, this kind of training is still considered self-supervised, right?
Exactly. Because it's using the data itself to supervise its own learning process.
Okay, now, probably the most fascinating thing we've discussed is this concept of an agent behavior. These models, they were mainly trained to predict the next word, but then suddenly they can do all these other amazing things. What's going on there?
This is where it gets really interesting, and it's still an active area of research. We call it emergent behavior because these abilities, they kind of emerge spontaneously. The models weren't programmed to do these things.
Right.
So things like translation, writing different kinds of content, summarizing long articles, even answering tough questions, these are all really complex tasks, but these models can often do them really well. And it's not because someone explicitly coded them to do it. It seems to happen as a result of just how much data they're trained on and how powerful that transformer architecture is at finding patterns in the data.
So it's like By learning the deep structure of language so well, they develop a kind of general intelligence for language tasks.
Exactly. It's a testament to the power of scale and machine learning and the flexibility of the transformer.
Yeah.
But the exact mechanisms behind emergent behavior, we're still figuring those out. It's an ongoing research puzzle.
Well, as you can see, this deep dive has uncovered a lot. We've gone from the basics of the transformer to the incredibly powerful GPT models we have today. The shift to unsupervised learning, the sheer scale of data, this whole concept of emergent behavior, it all points to a future of rapid innovation with huge implications. Hopefully, this has given everyone a better understanding of this complex and rapidly evolving field.
It's been really exciting to see how these different pieces, the new architecture, the self-supervised learning, the massive amounts of data and computing power, how they've all come together to create these incredibly versatile tools. The pace of progress is just amazing.
Now, before we go, we want to give a warm welcome to all the listeners tuning in from the Femtoware AI podcast.
And as we think about the bigger picture, it's clear that these advancements are already changing how we interact with information and technology, and that impact is only going to grow.
And for all of you listening over at Femtor AI, here's something to ponder. Given how quickly these language models are advancing, what's the one application or use case that you think will be the most impactful or transformative in the next few years?
That's a great question. It forces us to look beyond the hype and think about the long-term societal effects of these technologies.
Well, thank you so much for joining us for this deep dive. We encourage you to keep learning about this fascinating field, maybe even check out some of the research papers we've mentioned. There's always something new to discover, and AI never ceases to amaze us.
What strikes me is that we're really just at the beginning of understanding what these models can do, and who knows what incredible discoveries lie ahead.
Absolutely. Until our next deep dive, keep those questions coming.